This is a binomial expansion question. First of all, you need to write it in a different form. So 1 minus x to the minus 2, because now we can use the general formula for dealing with binomial expansion of rational coefficients, which is 1 plus nx plus n minus 1 over 2 factorial x squared. And then this pattern sort of just carries on. We're just asked for the first 4 terms, so that will do. Now, in our case, we need to replace plus x by minus x and n by minus 2. Okay, really important, so be careful with this that you do replace the minus x. Two factorial is just 2. This becomes minus x squared. Okay, so the double negative just leaves us with 1 plus 2x. This 2 cancels with the minus 2 and the other minus, and this becomes positive when you square minus x, so we get plus 3x squared. Here, the 3 factorial cancels with the minus 2 times minus 3, and the minus 4 will cancel with the triple minus that we get with the minus x all cubed, so that leaves us with plus 4x cubed. And those are the first 4 terms of this binomial expansion. Okay, pretty neat. Part 2, we're asked to write down the coefficient of x to the n. So we can see the coefficient of x cubed is 4, x squared is 3, always seems to be one more. So it's n plus 1. And I'm not just guessing, when we do the expansion we see that every time, well, you never get a negative because you always introduce a new negative and another negative here, so that always cancels. And as we increase, so if the next one will be minus 5, but then I would divide by 4 as well, so you can just sort of see extra time every time it's this extra coefficient, it's getting increasingly larger in the negative direction, but cancelling out with this negative means it's getting increasingly larger in the positive direction. Right, for the next part, we're asked to show that this is true. Well, let's focus first of all on what we already have and look at the summation. So actually, we've kind of just proven in A that 1 over 1 minus x all squared is this thing, and it's going to carry on, and that actually is going to be an infinite summation. So let's go from n equals 1, because the question has n equals 1 in it, up to infinity. Just need to carefully think about the terms now. So if we put in x to the n, then this would be, the first term would be x, because it would be x to the 1 plus x squared plus x cubed, and so on. Now I want my first term to be 1, in fact, so we need to make it n minus 1 here. And now then it'll be 1 plus x squared, and so on. Okay, and now finally we just need these coefficients, and we said in part 2 that basically the coefficient of x to the n is n plus 1, so the coefficient of x to the n minus 1 is then n. And this will give the required summation. The first term will be 1, the second one will be 2x. When you put in 2, then 3x cubed, and so on. So this is crucial. We've got something slightly different that we're asked for. So if we're summing from n equals 1 to infinity of x to the n, Well, we want to be able to use this top line, and we can do that if we just manipulate this expression slightly. So it's going to be nx to the n minus 1 if we sort of take out one of the x's, and then we're just going to have to times by it. Now, because it's not the dummy variable, it's not in the summation, we can actually take it out and multiply it by it afterwards. And we've just said that this thing here is equal to 1 over 1 minus x all squared, and therefore the final answer is going to be x over 1 minus x all squared, which is what we're expected to prove. Okay, good job. Moving on to part C. Slowly, we're making it more complicated. You can see where we're ending up. Right at the end, we've got this, this fairly complicated summation, but we would have proved some stronger results earlier on that we can then use, presumably anyway. So part C, we're asked to prove for modulus of x less than 1 that this is equal to the right-hand side. Well, okay, let's start with the expression. Okay, we can separate this into two parts. So I'm going to, first of all, it's going to be a n x to the n. And then x to the n here. Now this expression is just going to be the sum. Actually, I'm just going to change the color. We can actually take the a out of this one and make it nx to the n. And we just showed this result a minute ago. That is equal to x over 1 minus x all squared. And then this one is going to equal, I'm just going to put a line down the middle. Right, we don't have a result for that. We've shown some things, but nothing for this at the moment. Well, this is a geometric series rather. So my first term is going to be x, then x squared, x cubed, and so on. So geometric series, a is equal to x, r is also equal to x, we're times them by x every time. And the sum to infinity is a over 1 minus r, which is x over 1 minus x. So back to the main thing. This is equal to ax over 1 minus x all squared plus x over 1 minus x. Now we're asked to write it like this, so we clearly need to put it over a common denominator. Yeah, put it here. Right, so this one stays the same. Here I times top and bottom by 1 minus x. Add them together. And finally, I can see that there's a common factor of x, so it's going to be a plus 1 times x. I factorize the x out, just put it after the bracket instead of before, minus x squared all over 1 minus x all squared. That is what we're asked for, as you can see. This leaves us with the very last part. Hence, so this is basically saying use what we've done already to find the answer to this summation. Now, there's definitely some similarity between this and this, and if we can get it in the same form, we can use that final formula that we've just obtained. So we can write it as 5n plus 1 times 2 to the minus 3n. And this is nearly there actually, because we just need x to the n, so we can change it. We can change 2 to the minus 3n to 2 to the minus 3 to the power n, which is 1 over 2 cubed, which is 1 over 8 to the n. Okay, so this will equal, we can replace a by 5 and then x by 1 over 8. So we've got 6 times 1 over 8, that's going to be 6 over 8 or 3/4. 1/8 squared is 1 over 64. All over 7/8 squared, which will be 49 over 64. Okay, I could put these over a common denominator. Do you know what? I might do that actually. Or I could sort of divide by this and deal with it. Doesn't really matter. So times top and bottom by 16. So that'll be 48 over 64. Which will be 47 over 64 times, and I'm dividing by this, so it's the same as times in by 64 over 49, and this gives us our answer, 47 over 49. So not too bad actually, once you realise to write it in the form of the previous question, we can evaluate it. Pretty neat, because that does not look easy to evaluate when you first look at it, but we've proven these strong results to allow us to. Brilliant.